So the k-nearest neighbor classifier is a what we call a non-parametric model. So we talked about we have supervised and unsupervised. So if you think of it mathematically, as you're trying to build some function or a probability function, even for more advanced ones, where what's the probability of this being the correct label for the data given some parameters or features, right? So we'll often also use theta as, well, they're the parameters of the model. And so, like I said, for this KNN one, we've got K for neural networks. There's lots of parameters. These are the actual parameters of the model, right? So in your algorithm, you've got parameters that need to be set, and you have to set those. So that defines how your function is going to work. And then you give it the training data and the labeled data, and you build a probability distribution or a discrete function that tells you, right? Unsupervised, you don't have that Y, so you're just trying to build a model of the data. But then there's this question of whether you have parameters, whether it's parametric or not, right? So you always have some parameters you're going to set. It's a confusing name for this because non-parametric models still have parameters, but the thing is that the parameters don't scale with the data, right? Yeah, so in parametric ones, they are fixed, right? So neural networks and some of these other ones we're going to talk about, linear regression, right? So you think of, if you're familiar with linear regression, we will review it a bit, but it'd be good if you know that already. You essentially, you set a bunch of parameters, for different aspects of the data, and you set a bunch of those, right? So all of these methods, there's a fixed number of parameters that are used. You set some function, and then you learn the data, right? We're going to talk about these kind of analytical methods next week, which lets you basically, if you have a closed form version of this, of your function, then you can kind of optimize it and get the perfect answer. That's not usually possible in the more complex ones, but it is possible kind of in these simpler models. So that's parametric. So you'd think non-parametric would be something that has no parameters at all, right? That's not true. Non-parametric just means that the parameters is not fixed, right? The number of parameters is not fixed. They can grow. And so the one we're going to talk about is like that, k-nearest neighbors, because basically as you get more data, you get more parameters. So you have data essentially for every small group of data points, or it's adaptable to the size of the data, and it can become more and more flexible, right? So this makes them very powerful because they can basically expand as the data goes. What else would happen with that? You're kind of expanding the number of parameters you have, and the parameters designing a function that helps you map from the data to labels. That gives you more flexibility as you go. Is there any drawbacks that could be to that? Let's try to have a question and answer. Right, stuff is right. If it'll slow things down, right? So it could be slower training time. It could be even slower testing time. So if you're adding parameters to your model as the data arrives, your model is going to get bigger and bigger the more data you have, right? K-nearest neighbors and decision trees are like this because as you add more data, you add more split points and kind of ways of defining your function, right? Whereas models that are fixed number, the model doesn't get more complex as you get more data. And when I talk about scale of the data, I'm just talking really about number of data points, so rows in your table, right? How big is the data? but the number of dimensions is also relevant. Things get more complex as you get more dimensions, but it doesn't necessarily slow your model down. It just makes the problem harder, right? But more data points, if you have a non-parametric model, your algorithm will actually be slower because it needs to fit a bunch for each. Right, so people are asking about what kind of parameters could we be talking about. So in here's the carry neighbor's neighbor one, which is the first one we're talking about. And so here our function is we're basically trying to come up with the label, essentially as a kind of probability of whether this data point should have a label, this particular label or not. So does this household, do they have no cars or they have 2 cars, right? Which one are they? And we've got our data point. I keep changing the notation because I have different generations of slides. In my notation, I said D was the data. So it's just the data. But then K is your number of neighbors that you're going to use for your calculations, right? So just so people have this in their head if they haven't thought about it before, the idea is you have a bunch of data points spread around, and if you've said, okay, K equals 3, I'm going to use K equals 3 neighbors. For every data point, you say, I'm going to assign data points, I'm going to come up with a distribution for any point in space, in the data space, having a label based on the proximity of the nearby points, right? So you have labeled points, right? So the 1s and the 0s, or the red ones and the blue circles here, are 2 sets of data points that are labeled with 1 and 0. That's the class they're in. And so if we get a new data point here, literally at this spot, we say, well, if there were a data point here, which class would it be in? So you compute, you find the 3 nearest points in the data set, and you use the ratios of them, right? So you basically compute a probability of like which one has the most, right? For that label. So the probability of a point here being class 1 is 2/3 because these guys are slightly closer than that one, and you're using 3 labels, 3 nearest points, right? So you imagine now if you set K equal to 4, then for this data point we'd have to find, I think this one's the next closest point. You'd have to use those 4 points, and so you'd get a different answer, right? So that's a parameter. That's an example of data, right? So people were asking about other ones. So if you're familiar with neural networks, every weight in the network is right. In a neural network, we've got a bunch of nodes, and don't worry, we will do neural networks from scratch if you don't know them. But the idea is you have input data and you have a bunch of nodes along the way which do some calculations, and then you have an output which helps you get some classification, say, right? And every, if I double click on a line, it opens this helpful dialog. So along the way here, usually these are called W, right, in all of the layers. What a node does is that it says, so whatever, one of these nodes, it sums up all the data points and all the inputs from the previous layer and combines them together, right? So these weights are the parameters in a neural network model. So a neural network is useful because it has lots of parameters, far too many, more than it needs to fit a function. It's kind of under-constrained. That's why it can fit any function. But that's why it took people years to figure out how to train them properly, because obviously you can fit a function with a neural network. It has more than enough parameters to fit anything you like. But it's tricky to do it in a way that's efficient and generalizable. Luckily for you guys, everyone figured that out in the last 10 years or so, and so now they can be trained for anything. But they are kind of maybe overkill for some problems, and the fundamentals of it, like I was going to say, as we'll get to later, in the original formulation of neural networks, essentially every one of these little links here, well, every one of these nodes with its inputs is like logistic regression, but they've combined them all together. Since then, they found out that that formulation isn't the best way. So, but the essence of it doesn't change. The parameters are all the weights, right? And in decision trees, since we're talking about parameters right now, and decision trees is the other good example, which we'll do in a couple weeks. Every time you get a new data point, you make a split, and you have another set of data points, and essentially you break up the data into like little tables so that all these, you partition the data into little different groups, and then you make a prediction about each subgroup at the leaves, right? And with some smaller set of the table, right? And so in this case, all of these splits are decisions. Like, okay, take feature number 2, and if it's less than 10.3, then go left. If it's greater, then go right, right? So that's the parameters in decision tree. So the parameters for each algorithm are completely different concepts, but that's how their power comes, because they all do very different things in the data space. All right, let's see if people had concept responses to that. The parameter, as someone's saying, the parameters in the model are what we're training. So when I say, that's a very essential point. When we say here, that's the parameters of the model, the parameters are what you are training, yeah. So we're talking about this equation now. Somebody's asked me to explain an equation. If you meant a previous one, let me know which one. For k-nearest neighbors, though, our first one, we have this. That's what we want, right? So it's distributions. We want to pick a class given these given the different settings we have. And I explained it to you kind of logically, but what you're really doing then, what does that even mean? Sorry, my math there looks weird. The only thing I'm trying to work out is, what's my epsilon here mean? That kind of slipped in when I was editing the slide, I think. Fraction, highest probability. Yeah, so the main idea, and maybe I can just turn off. I'm sure there's a way to hide notes. I know there is. The idea is that we've got the number of neighbors for every point. That's the set of neighbors. And then remember the indicator function, right? So indicator function will say it's only true if they equal the class, right? So for every one of your neighbors, basically it'll be 1 if it's in the correct class that you're looking at. So we're trying to right now calculate the probability of the family having 1 car. So for y equals 1, given all the data points, how likely is it for every x that you give it? And so the neighbors around you that are not in that class would be 0 from the indicator function, right? So this would be 0. And then from the set, you'd get only those neighbors that are the ones around you. And then the mysterious epsilon, which changed from something else. What you have to basically do is compute just the count of how many there are, right? And we divide that by k. So yeah, what I would say here is change this to be this, and say that we just would count the number of elements in the set that are in that class, right? And so we use that as the number, and then we get that over k. And so if there's 2 in that class, you get 2/3. But you do this for all of the data points and all of their neighbor sets, right? So that's why it's computationally expensive, right? Because for every data point, not just these data points, but any data point you're querying, you've got to compute it, right? Now, for the label data points, we don't need it because they're already got a label. But say now your test set are a bunch of data points in these arbitrary places, right? And you want to know what class they're in. And so for every one of these, you've got to get its 3 nearest neighbors and compute its ratio, and then you can pick the one that's the highest, or you can just report the whole distribution and show that to people. So for every data point in your test set, you've got to compute you've got to find the 3 neighbors and compute this ratio, right? And so if you could take, if you've taken 606, some of the graph theory kind of algorithms you talked there about, shortest path and like covering graphs, you could use those to figure out which the neighbors are, which you know yourselves from that. Those are computationally complex as well, right? So this is not necessarily the most efficient algorithm because getting the neighborhood and computing these things can be challenging. And then as you scale it, the more data points you're using, the bigger it is, the more data points you're querying about, you have to compute them for more. So it's a very kind of simple and powerful, it's a good comparison method, right? So if you're building your own classification algorithm, it's always good to compare against KNN because it's quite powerful, even though it's very simple, but it is a bit expensive sometimes. And it's not as complex or as effective as like decision networks or decision trees or neural networks usually. But maybe your data is simpler than you thought, right? So once you convert your features and into a usable space and everything's nearby, it might be sufficient. So one way of thinking what it really does is, because like I'm saying, you've got data points here. The points on this diagram, I don't know if you can see the color, there's dark ones and red ones. So those are the 2 classes. And the idea is you basically divide up the entire space of the features into a Voronoi diagram or a partition space. So here we're only showing 2 dimensions. Say we have a 2-dimensional data set. Right, so these are all the training data, right? For every training point, there's a point in there, and essentially it's the master of an entire domain in the space, right? So if we ever have a test point somewhere else, and we want to know which one's closest, it's going to be this one, right? So if you could pre-compute the neighbors and the right choice for every point in the space continuously, you'd get this diagram. You don't want to do that necessarily if it's expensive. But some of the ways that make KNN faster, they'd use kind of geometric tricks. Essentially, they do draw this diagram, and then you just query the spot, and you figure out, well, which polygon am I in, and you say that's the class, right? But computing this is expensive, right? Oh, maybe he's right. Somebody, Jan had a good point. If I lost my eye there, that could explain it. I was trying to think what it could be. I mean, essentially, we want to know the number of points that are in this set, right? But another way to do it, and I'll fix this slide after, is to say, give me the index of all the points in this set, and if it's 0, then you divide by 0. Well, we don't want to have the number. I don't know if that does it either. We still only want the count, right? We only want to say how many points are there. So I think it's still better to say what's the size of this? But I'll fix the notation. In your code, you understand what you're saying, right? It's like how many points are there, and you're coming up with these ratios. Hopefully that is clear. Oh, that's a very good question, right? So what if it's split? Right? What if it's 50% and you can't tell? Then you can't tell, right? If it's equal and you basically are in the middle, and this point, well, that's not a good example. Some data point is kind of in between all of them and you can't tell, then you don't have enough information to make classification, so you could randomly choose. For every implementation of a KNN algorithm, there has to be a tiebreaker that would say, how do you determine the right class if you don't have enough data? And there's no right answer necessarily. So my suggestion, if k is always odd, then that wouldn't happen. I suppose that's true. But people use even numbers of it. And if k is a higher number, right, so if it's 10 or 20, then even if it isn't technically equal, you might still say, well, it's quite close, so we wouldn't necessarily want to say they're different classes. But you can also just report that distribution, right? So what are we showing here? This is k, yeah. So one thing you can do is, rather than just making a clear saying, oh, it has to be this class, because maybe what you really want is an understanding of the space, right? So given this data set, and this is from the scikit-learn's page for the scikit-learn package for KNN. I think they have this plot on there. Can you see my mouse? Yeah. There's three data sets here, right? So we've got the blue ones and the green ones that are X's, and the red ones that are crosses, and the blue ones that are stars, if you can't see the colors. And so some kind of clear, like if I was going to separate them, I would draw a line like this and say, okay, those are the three classes, and with some error, but it's pretty good. So I'm agreeing with, I guess, the model. If you make me choose just one label, that's what I would choose. And it said maybe like this, so I guess that's a good point because there's no X's here, right? So you could come up with your own line, but you don't have to report that. You could report the entire distribution, right? So for all of the classes, you've got 10, now k equals 10. That means you've got 10 probabilities, so every one you count the number of neighbors, and then you say that over 10, and then you can report that as a probability and give a color, and so it's saying, this is, I don't know if you can see that text there. You should be able to zoom in. That's the probability that the class is class 1, given the data, with 10 neighbors, right? And okay, so this is 1, right? So the data sets are labeled this way. That's 1, that's 2, that's 3. And so if you say, well, how likely is it that any data point should actually be in class 1, and then you scan over all the points and compute those probabilities, you get this, this chart, right? And so that matches what you'd expect. It gives you kind of a probability distribution of every spot in which class it thinks it should be in. But then you don't have to worry about ties because you're just reporting the probability, right? And then if we'd said, what's the probability of class 2, it's this one, right? And that gives you how likely are you to be in this class. So for a simple method, it's quite rich in terms of what it'll give you in the output, right? Good. People throwing out different ways you could solve these problems. And as you're doing them, so that's the whole, that idea of validation step, right, of saying, you know, what should k be, right? You don't want to commit ahead of time to k being 3 here, because you're going to get not a very good model. 10 seems to be quite nice here, but maybe you want to try out a bunch of different k's on your validation set, And then once you've picked it, you throw that away, right? Let's say we got 10% of our data, and we got 80% of our data for training, and 10% of our data for testing. We try out all the different k's until we say, oh, k equal 10 is good, and then we throw this out and we train and test on the rest of your data, right? That's kind of one of the reasons we have it, because you don't want to commit ahead of time to that. But there are other models that are adaptive, and so k doesn't have to be a parameter. In k-nearest neighbors it is, but you could have other classification algorithms where it says you could adaptively say, if it's starting to look like one of the classes is really weird and has a very high variance, you increase the number and recompute some things, right? The poll is covering the slide. Usually when you click on the side things for the chat or the poll or the people, you can make it go away. At least that's what happens with me. What do people say? Okay, so data problems are well distributed across the world. That was the answer. Great. Okay, so comments on this. So non-parametric, because does anybody understand why it's non-parametric? Right, so we've got to do those calculations for the neighbors of every data point you're asking about, right? So it's a non-parametric in the test set. As you add more tests, as your test set increases, the number of calculations you have to do increases by kind of a fixed amount. It has bias before its classes have more samples. So if some class is really good and spread out all over the place, you're often going to think it's the one. And you could think about how sensitive it is to noise, right? So if all of a sudden now you've got this model and then I add one more, well, no, that's not a good point. What if I added a blue class 2 point over here? All of a sudden the whole model would change, right? It would change everything. All these pictures would change drastically, right? Because now some of these data points might have a nearest neighbor. Maybe that's not the best example. You got to have one like closer in to all the other data points, but you could have some data points could skew it quite dramatically, which is something that happens in a lot of algorithms, so that's not unique. So ways we could try to fix this, right, to speed things up, is to say get rid of redundant points. So if a lot of points are all clustered together, maybe we just get rid of some of them, right? So you could say, let's just thin it out in the dense areas, because you're never going to use, if there's a bunch of data points here, and then they're like this, nobody outside this little neighborhood is ever going to use these inside guys, right? Because they'll always have one of these as their neighbors. So you could thin things out and speed up things quite a lot. And you could compute your distance in a clever way, so it doesn't have to use all of the data, all the features. You could also transform the data into a different dimensional, like a lower dimension. That actually helps a lot. And you could combine other algorithms. So there's different things you could do to speed it up. Good question. KNN is a lazy learner, so it's not training. Yeah, that's right. I mean, because the parameter we're setting is the k, and it's kind of inherent in the model, right? Because the this graph, once you've picked k, this graph is implicit in the data, right? And you can compute it. You could either pre-compute it or you can compute it based on as you need it. So as somebody saying, there's lazy learner is one way you could describe it. So you're not really training a model that learns and then new data changes it. If you added more data to your test set or once it's labeled, it would change the graph though, like if you were given more labels. But in a sense, it's not training in the same sense as a decision tree or a neural network are, because the weights don't change after, once you're given the data, they're fixed. That's a good point. Good. Okay, so we have a little bit of time left. The other model that we had here was a simple model for density estimation. And this one is also non-parametric, but it uses the density of the points in some area, right? So kind of rather than doing like a neighborhood calculation and counting them, you could talk about, well, how near are they to each other, right? So we do the same kind of thing, but instead of saying now for some data point x, what's the ratio of like nearest points to it, we define kind of a bandwidth distance that we're willing to look around us with some kind of shape. And then we say for distances from this point to all the other points, it's kind of implicitly done in nearest neighbors, but you get rid of all the zeros. So we say, well, how far are we from all the other points? And so for every one of those, we'll divide it by this bandwidth. So we're scaling it by a certain size that we're kind of more interested in. And then we combine those together, but we also combine them together with what we'll call a kernel function, which will come up again and again in different methods. We'll talk about it again in the dimensionality reduction week, as well as support vector machines. And so a kernel function is a function that maps data points from one space to another, right? So in this case, we're mapping points to the Gaussian distribution, right? The normal distribution. And so we say you've got your x, and then we're setting it to some value y, given the normal distribution, right? And so we're shifting the mean and the standard deviation to match something from the data. So in this case, the mean of every one of these kernels is the data point we're giving it. So we compute this kind of distance here. We use that as the mean, and then the standard deviation we get from that data set as well. But we can choose different functions for this, right? So if we're using the Gaussian, then we're going to use Gaussian formulation. If we want to have something simpler, we could use our indicator function again and just say, as long as there's the value of this is less than 1, then we include it, right? So since we're computing the distance to points here, a boxcar would be saying like, okay, any points that are kind of after we do these calculations and use the this bandwidth h, if it's still less than 1 away, then we'll include the point. If not, then we won't. And so you'd get zeros and ones for that. And then we do the same thing as in k-means, that whatever number we get out of this is going to be more of a continuous number. So it might take contributions from multiple near-ish points, and maybe only some portion of them because it's using a Gaussian. We'll sum those together and then normalize it by the number of points, but then also by this bandwidth h, which tells us how big our view is. And so if we see a couple different views of this, here h is equal to 1 and h equals 2. And the kernels, you can use just a uniform kernel or a Gaussian kernel. And essentially you're saying for every data point, which class should it belong to? In this case, I don't have the class listed there. But you'd also need then a threshold that tells you that if you're above some number, that it'll be in some class. Below another number, it'll be in a different class. I believe that's how we do it. So it takes some of that idea from k-means, but does it in a more continuous space. And like we said, this kernel can be kind of chosen to give you different shapes. So you're essentially doing the same thing, right? The points are closer together here, so they're more likely to be in the same class. But you could spread it out a bit, right, with these different functions, and you could use any probability distribution that works there or any function. So that's kind of a more continuous version of that. Right, and so we can define k nearest neighbors using KDD. Where essentially, so one of the, I guess, the simplifications of the Parzen Windmill process is only one bandwidth for all the points. It's the same actual space around them, whereas in k nearest neighbors, it's actually adaptive, right? Because your neighborhood is not a fixed space, right? It's the number of them, right? So if they're far apart, it's still these guys, right? Even though someone else, they're close together, it's now a different thing, right? Whereas the window approach, it's essentially a certain size in the space, and it's fixed. But you could have a window for every data point, and then it's very similar to KNN, but with these kernels on top that essentially say, I don't even just care about that. I maybe, if these points are nearby, we've got a kind of a Gaussian, if this is the second standard deviation gradient of your Gaussian, viewing it kind of in 3D, you could take some of the contributions from these guys as well, right? But they'd be smaller because they're further away. So you wouldn't be fixed to a number, you'd be fixed to a kind of a shape around it. So good question about whether data points that are far away will give you 0. It all depends on the function you set up, right? So if it's a Gaussian, it wouldn't really go to 0. They never go to 0 entirely. They just get very, very small, right? So you would have the point that these are kind of way down there. And so, yeah, you're computing it on all the points and to be small contributions, which might be good if there's thousands of points over here, they would all build up and you get some sense that, well, maybe it is likely I'm just an outlier. But if you want one that drops off differently and that actually goes to 0, you could pick a different distribution, right? That's why these fixed window boxcar things are more like strict, but any function that works. Okay, you're welcome. So that's the end of those slides. I thought I might go faster, but that was good. We did lots of good questions and discussion, which is kind of why I want to do this stuff live, if that's helpful for people. Now, hopefully the recording has worked. I've been recording it separately, so I will stop that and then see which one saved and put them up on YouTube. And then tomorrow we will talk about these performance evaluation curves, methods for saying, is your classifier working well or not, and that kind of thing. These slides are already up there if you want to take a look. And we'll talk about some of the ways we can evaluate whether a classifier is working or not. Because basically we're introducing the idea of classification and supervised learning here, give you a first classifier, and then we're going to go through other methods like map and MLE and dimensionality reduction, and then later on we'll do many other classification supervised learning methods, but we'll kind of give you a couple algorithms to start so you can use all these more pre-processing and analysis tools on them. So that's where we're going to end, and thanks everyone for your questions. If you have other questions, Piazza is the best place because then any of the TAs can respond. Thank you, Julie. And Piazza is much better than email because I'll probably lose things in the email. So we'll talk to you on Piazza and we'll get some of those other things sorted today with houses and feedback, and I'm gonna solve the video saving issue as soon as I can. Thank you everyone for your patience and talk to you next time.